Now lambda may or may not be in S, but I claim that there are infinitely, given any epsilon, within a neighborhood, an epsilon neighborhood of lambda, that is to say, within this interval about, symmetric interval about lambda, I claim there are infinitely many points of S. Were that not true, I can go far enough out with my INs to put an IN inside this, couldn't I? All I have to do is I think, let n be big enough so that 1 over 2 to the n is smaller than epsilon, and then my I sub n gets inside this guy. But remember how these were constructed. I just went with the infinite subset each time. All right, that means there's infinitely many points of S within epsilon of lambda. And that, friends, is a limit point. Point of accumulation. Definition of a limit point, there's some, those two things mean the same thing. Accumulation point, limit point. A limit point is not a limit. A limit point is a geometric object, which, if you take a neighborhood of the point, there are infinitely many points of some set within it. Right? This is in the context of real numbers. If you guys are taking topology, which I would love to teach, there's an even more basic definition. Let me give you the basic definition. It reverts to that in the case of the real numbers. A limit point, in the general topological sense, is this. It's a point such that if you surround it with an open set O that belongs to a topology. A topology is a collection of open sets. If you have this point lambda here, what you insist lambda to be, if you want it to be a limit point of the set S, it means there must be, for every open set in the topology containing lambda, there must be a point of the set S within that open set. Distinct from lambda, it's entirely possible that lambda is also part of S. You can have, even with the real numbers, a single point, and then a whole bunch of a connected interval over here, a single point over here, distinct from those, or out, away from those. That's not a limit point of the set. It's an isolated point. There's a little open interval around it that contains no other points of the set S other than itself. It's in the set S simply by definition. We say you're in, but nobody next to you is in. So you're isolated. If there's always a neighbor infinitely close to you, you're a limit point. If you're a set and you consist of nothing but limit points, in other words, no isolated points, you're a perfect set. Okay? You're a perfect set. All right. So there's a little topology of the real numbers. And are we accepting my graphical proof here? We chew our way down. The intervals get shorter and shorter. They're closed. They're nested. That satisfies the nested interval theorem. There's a common point lambda. I claim lambda is a limit point. Why? Because one of these guys will eventually get inside every open interval surrounding lambda. That means it's a limit point. So bounded infinite sets of reals have limit points. Now, if it's a closed set, a closed set contains all of its limit points. So it would necessarily have to be in the set S. If you're closed, all your accumulation points or limit points are within your U as a set, right? So lambda would be part of S. All right. So that's the Bolzano-Weierstrass theorem. Going to need that for the Cauchy theorem here in a couple of different ways. The Bolzano-Weierstrass theorem creates limits. Because if you have a limit point, you can make a sequence converge. So it kind of, you push a button on boson or wire straws, and it gives you a candidate for the limit of a sequence of points in your set. If you need to, for some analytical purpose, have a sequence converging there in your set, then you have it. In fact, sequential compactness, let me define that for you. A set is sequentially compact if every sequence has a convergent subsequence. Right? So, is the set of natural numbers sequentially compact? Nope. 1, 2, 3, 4, 5, 6, 7. That's not going anywhere, right? No limit points. It's an infinite set, but it's not bounded. You've got to be bounded. Sequential compactness is, again, definition of sequential compactness is a set is sequentially compact if every sequence in the set has a convergent subsequence. And as I said, that's the general definition. In the real numbers, sequentially compact and compact are the same thing. I guess we better get compact on the paper. A set is compact if, whenever this set, let's make O for open, and the index set here can be huge. It does not necessarily have to be counted. In fact, when we prove Linus theorem, our index set will not be counted. So I have potentially some gigantic collection of open sets. So if I have a bunch of those open sets and K is contained inside their union, okay, that implies that there exists a finite number such that K is still contained in the So in other words, if you have an arbitrary number of open sets that cover a set, if you can always find a finite number that will still do the job, that said that K is said to be compact, K for compact. My dear dissertation advisor, may he rest in peace. This is like a very distinguished analyst from Germany, old school guy, trying to teach this to analysis 1 people at FAU. And he was very proud of the way at lunch. He said, I finally figured out how to explain compactness. It's like, and it's Boca Raton, beaches and all that kind of stuff. He said, suppose you have a person laying on the beach, and there's a whole mess of towels, uncountable number of towels on the beach, covering up this person. Okay. If you could remove all but finitely many of the towels, and the person is still covered up, then the set that that person represents is compact. Okay. Well, strange metaphor, but he liked it. He was very proud of himself. He made it practical. So the idea is to have a cover that's reduced, an open cover that's reducible to a finite sum, right? Said quickly and efficiently, a set is compact if every arbitrary open cover of the set can be reduced to a finite sum. That's called the Borel-Vague criteria. Notice how these names keep coming up. Yeah. The Borel-Vague criterion for compactness. Every arbitrary open cover is reducible to a finite sum. There are other criteria, but would need a lot more definitions, and they all, they coalesce. The idea is to frame it some different way and show that the two definitions are equal. And some of them are just I won't confuse you. Some of them are just really off the wall. Have to do with projections and parallel spaces. And this is closing. Oh my God. I don't remember them all. The one that everybody remembers and knows is this one. Morel-Bay criterion, phrased in terms of golden colors. Okay? So, let's talk about what sets of real numbers could not possibly be compound.